So my talk, I would like to divide it into two parts. The first part is actually this paper, these two papers. It's a little bit old, so like 2013 is gravitational decoherence, and 2015 the gravitational cat state. I'm going to spend hopefully just 20 minutes not going into any technical details, but highlight the essential points which you can see actually bear on the same theme, that is fluctuations. In particular, the quantum field fluctuations and how that would impact on gravity, and vice versa. That is, if we're dealing with a gravitational field, how do we look into the fluctuations? That's the gravitational noise. That's the second part. The second part would be, well, hopefully 30 minutes or so. I'll go into a lot of technical details. So if you excuse me, the very stark contrast between these two parts. All right, so let's start. Let me adjust the view because the view is blocking my view of the slides. Okay, much better. Thank you. All right, so the quantum field theory in curved space-time. In the next slide, I'll go into slightly more details. Of course, started with quantum field theory and general relativity. But I would like to also add on a very important element or basis factor, quantum information. That started about 95 or so. And these three components actually are playing a very dynamic, interactive role in many of the current research bearing on gravity and quantum. Okay, I want to say that this has nothing to do with quantum gravity, which I define, and I think most people would agree with me. Quantum gravity proper refers to theories of the fundamental structures of space-time, and it would be the Planck scale effects. What I'm going to talk about, these three processes, which I just mentioned: gravitational decoherence, gravitational cat state, and gravitation or graviton noise. They're not Planck scale. They do not need to be Planck scale. And I think that is actually more fruitful because even in today's low energy, ultra low energy, I would say, there are experimental methods and even experiments, existing experiments, wherein we could check the theories that we develop. Okay, so there are three components I'd like to bring back to the 90s, as Bob yesterday mentioned many times, 25 years ago. Okay, so in fact, if you count 72, it was 50 years ago. All right. The first part is what everybody is familiar with. I would just top a little bit over with the semiclassical gravity going into stochastic semiclassical gravity, which started around 95, 94, okay? But also there's an important element in terms of the theoretical basis that we need, which is non-equilibrium quantum processes. That by itself, of course, has a wide range of relevance to many important physical phenomena. So the non-equilibrium quantum field theory is one part, but in particular, the method that we've pursued or used in the last 20, 30 years is known as quantum open systems, okay? The two are interrelated. I would attribute a little bit more of the Boltzmann philosophy behind non-equilibrium, meaning that is we're dealing with a democratic system. On the other hand, if you're lucky enough to deal with situations wherein the system can be judiciously chosen and well-defined, then you can use the open quantum system approach, which usually is attached with the Langevin paradigm. And in particular, especially in application to the early universe and black hole processes, the non-Markovian processes, where in memory becomes important. As I mentioned, around 95, one could say that quantum information, which of course now has mushroomed in many good ways, seeping into almost all areas of fundamental theory in physics. Okay, all right. So this is something that we're all familiar with. Roughly in the 70s, I started with even in the 60s with Leonard Parker's thesis, and probably best known in Hawking's 74 radiation, black hole radiation paper. And then in the 80s, well, even in the 70s, late 70s, after we've sort of were all satisfied with the regularization methods, then the back reaction problem started to take off in full steam, which went on in the 80s. And then in the 90s, the stochastic gravity. You can look at it in a very simple way, right? Sometimes people say, well, you just added a noise there. It's not so easy to add a stochastic term in such a beautiful theory, which is, of course, unitary and with all the nice features of general relativity, and then adding on quantum field theory, how you manage with quantum field theory in curved spacetime, so on and so forth. And so when people say that, well, it's easy to put in a noise, I say, well, it's easy to put an angular bracket around T mu nu. Why did it take so long for people to come up with a back reaction problem? So it took some time to develop all these theories, and then it's been applied to many problems. And I think if you look at the black hole information and literature, I think at the end, people would agree on one thing, even though there are half a dozen different ways of looking at things, or even stark contrasts in their philosophy and approach. They would all agree on the semiclassical gravity as a common denominator. So with that, let's turn to quantum information. And I would just focus on two fundamental issues, decoherence and entanglement. In particular, since we're dealing with quantum open systems, how would the environment affect the quantum coherence of a system? And as far as entanglement is concerned, how an entangled state evolves under the influence of its environment. Okay. Now, since our major concern is gravity or relativity, in the last 10 or 15 years, there's also a new field which emerged, which is called relativistic RQI, quantum information, with special or general relativity of gravity. So it's within this context that I would just give you a summary of what we've learned about gravitational decoherence. The work started about 10 years ago, and then gravitational cat state about 7-8 years ago. Okay, and this is a hot topic now because of many experimental proposals, tabletop experiments, primarily from the ingenuity and audacity or boldness of our AMO atomic optical physics colleagues. So this talk, as I mentioned, there are two parts, and I would be spending a little bit more time in this part, and relatively, I would jump across many technical details in the second part, because if you understand the influence functional method applied to quantum Brownian motion, this is the generic sort of base theory in non-equilibrium statistical mechanics, in particular, the open quantum system approach, it's rather easy to understand how to come up with a, well, first, how do you deal with the noise in gravitons? And secondly, its effect on the geodesic separation of two masses. Okay, so let's dig in. Let me summarize the key findings in gravitational decoherence, and then I'll just show you a few slides. It's by noises of gravitational origin. And why is this important? Well, gravity is ubiquitous. It's everywhere. You can't avoid it as long as you have mass. You need to deal with gravity. But in particular, since the 60s, there's something going on at the quantum physics side, on that side, and I would just group them as alternative quantum theories. Best known theories are the DOC-Penrose or the Garadi-Ramili-Weber-Pearl. I would also add on the younger colleague Bassi, okay, because he's done a lot of work and pushing this theory, continuous collapse theory, to the forefront. But here, okay, instead of changing gravity or quantum, we stay conservative at the level of quantum mechanics, meaning non-relativistic approximation of quantum field theory, and then GR, even just taking the weak field. Okay, so this is, of course, why I said even the tabletop experiments or near-Earth deep space experiments like LISA would be able to help in discerning some of the theoretical predictions. Okay, so the noise from weak gravitational perturbations of Minkowski space, it can't be any simpler. Okay, and we would only look at the dynamical degrees of freedom, meaning gravitons. Okay, now the big difference from these alternative quantum theories like DOC-Penrose or the Garadi-Ramili GRW Pearl, etc., is that gravitational decoherence is in the energy basis. Okay, whereas in order for their theories to work, they have to propose decoherence in the configuration space, localization in space. It's just another way of calling it the colloquial way of collapse of the wave function. So usually they have to introduce a length scale to divide what is quantum regime from the classical regime. And different ways were introduced. Oftentimes there's a stochastic noise that's sort of put in by hand for a specific purpose. We don't want to do it that way. We don't like that way of doing things. So we have to, of course, first find out what the noise is of gravitational origin. And we came up with the Lindblad equation, master equation, which is Markovian. It's the same as what Annapolis and I did in our 2013 CQG paper. In the same year, Miles Lenko used the influence functional method and derived the same master equation. All right, so I'll show you that equation in a minute. Okay, I wouldn't get into this part because there's also the so-called fundamental decoherence or quantum gravity decoherence, which people deal with decoherence at the Planck scale. Also, in most cases, invoking noise or stochastic sources in a somewhat, shall we say, purposeful or pragmatic or utilitarian way. Okay. All right, now the main feature from this ABH master equation is that the decoherence time is inversely proportional to a free parameter, which plays the role of temperature. Okay, and if you assume that everything is fine, fundamental, gravity is fundamental, and since we work with the Minkowski space time, it would be Planck scale naturally. Okay. But if gravity is emergent, okay, and there are many ways that you can explain why it is emergent, the theta is much lower. It's sort of like a temperature. And we all know that, of course, at very high temperature, decoherence time is very short, so on and so forth. So there's some chance of observing it. Or if you turn it around, if one day one could indeed observe gravitational decoherence, it's not easy, because how can you say that this is specifically due to gravity and not due to EM field, which usually overwhelms gravity, right, by many orders of magnitude. So this is still sort of in a hypothetical sense, hopefully in the future. Well, you can turn it around and try to decipher what this parameter is, and maybe that would imply a difference between gravity being fundamental or emergent. I'll just leave it like that. But another point that we use as a subtitle in our paper with Annapolis Harris 2013 is because we follow the quantum Brownian motion paradigm. And if you think about it, there are two parameters there. One is the temperature, of course. The other is actually spectral density of the environment. Here, the environment is the gravitational field. So I was thinking, what would that mean if one day we could actually see or estimate or decipher the spectral density of gravity, and we just call it the texture of space-time. I wouldn't say that that would enable us to see the microscopic structure, which I believe really we should wait. And that, of course, there are many theories of quantum gravity dealing with that aspect. But just like spectral density of harmonic oscillators, or if you think about dielectric, it's kind of a reflection of some mesostructure. In particular, it's causing the response of some system that's interacting with this environment, like this harmonic oscillator Brownian motion. But through Brownian motion, you can actually tell the spectral density of the environment. So in the same light, maybe there's some hope that we could probe into some mesostructure of space-time. Okay. All right. So here comes the quick skimming over. This is the mass equation. This, of course, since we're dealing with tensor quantity, this is the projection operator. If you look at that, that's just p squared, right? This is in full 4D. It's simpler if we just look at the 1D case. Let's blow it up a little bit, yeah. So this is p squared over 2m, right? That's energy, right? And it's kind of expected, like the case that we're more familiar with, the coherence, if you use a model which is like x and q, x the system variable, q the environmental variable, that would be decoherence in the configuration space. But gravity, of course, is coupled through energy momentum tensor. So it's no surprise at all that gravitational decoherence takes place in the energy spaces, which of course is fundamentally different from these AQT alternative quantum theories, wherein they would like to see the wave function collapse at some space-time point. And it's very different, okay? And here's this capital theta factor. So the decoherence time, you can see that is inversely proportional to a capital theta. And as I just said, it's actually also quite reasonable. In fact, without going through the mass equation, you can pretty much piece this up. This is sort of the Wheeler's poor man's way of approaching a problem. And in fact, in the way that Wheeler called poor man, you could pretty much use dimensional and come up with an answer before you do the calculation. So here's an example. All right, now I've said all that, so let's go to, well, this is a little bit philosophical. We don't need that, okay. Entanglement. So as some of you have followed Roger Penrose's work, he has emphasized this for decades. That is, there's an innate tension between quantum and gravity. Okay. Now, a central issue there, in my view, more important than gravitational decoherence, is this gravitational cat problem. Okay, because usually in quantum mechanics, time is fixed. Okay, for any manifold, but in gravity, that's a no-no, right? We don't want anything like that. So in order to even carry out the first step from quantum mechanics, if you take the viewpoint of general relativity, you're stuck there. Okay, there's just no way that you can do that. And that brings out this factor of the gravitational entanglement. So let me explain a little bit. The expectation value, right? If you take the, well, this just says that entanglement is probably the most important element, basic element in quantum information, because in fact, in quantum computation, that's the resource, okay? All right, so if you examine the expectation value, but not with respect to a vacuum state, but say with respect to a cat state in configuration space, let's say minus x and plus x, we should know right off that semiclassical gravity is not sufficient for dealing, with issues in quantum information, starting with entanglement, right? Because it gives the mean value of the stress energy tensor, which predicts wrongly that the cat is at x equals 0. There's no superposition, no quantum. So let's take a look at semiclassical gravity, because people say, oh, wow, you just strike it out in one short sentence. Well, if you look at semiclassical Einstein equation, here is the classical part, the general relativity, and here's the expectation value of the stress energy tensor of quantum fields, okay? And of course, the semiclassical gravity demands that the gravity part and the quantum field matter part should be consistent, okay? Self-consistent solution of the semiclassical Einstein equation as it stands here, okay? All right, but semiclassical theory can cope, right? It does not admit cat states, okay? And so quantum information in the face of gravity, if you start with the entanglement issue, we need to go beyond the mean field, okay? And we need to include fluctuations or correlations. It's actually two sides of the coin, because even in fluctuation dissipation theorem, there are different versions, one involving fluctuation, the other involving correlations, as you can see here, right? It's the correlation of the stress energy tensor are needed to address issues in quantum information with gravity. Okay, so that enters in RQI. And there is such a theory, which is the stochastic semiclassical gravity, which I touched on just now. It's actually the third rung when we build up from quantum field theory to semiclassical gravity, and now stochastic semiclassical gravity. The main difference, of course, is the introduction of noise and fluctuations in the quantum field. Still, classical gravity still remains classical, but in so doing, now how could you even allow the stochastic quantity into such a beautiful structure like the marble palace, okay, of general relativity, right? I mean, already Einstein said, well, on the right-hand side is sandstone. We're playing around with the sandstone and finding not just the average, but also the fluctuations in the sandstone, okay? That will become the Einstein Langevin Equation, which is the centerpiece of stochastic gravity. All right, so again, quickly, schematically, we have this QS here, right? So in addition to the vacuum expectation value or the quantum expectation value, we need a stochastic source, right? So that is the noise kernel. What is that? It's the expectation value of the 2-point correlations of stress energy tensor by tensor, right? So everything on this slide, in fact, with all these, what we did was everything is quantum field theory. However, there's a way that we could attribute stochastic features to it. And that was the crucial point, at least for me at that time. I was looking for something that's reasonable. I don't want to put in a stochastic term by hand, as is so customarily done, right? Even if you think about how we first learned Langevin equation, probably our teacher would say, well, here's the Newton's law, second law. Well, we'll put a noise term on there, white noise for simplicity. And then that just goes on. It becomes a Langevin equation, and we just look at its solution and so on. But where does that term come from, right? And in order to understand that, we really need the open quantum system framework for it. But anyway, so bypassing all that, here we follow quantum field theory. We don't just jump ship and introduce and bring in this strange stochastic term. It should not be done, is disallowed. Okay, so this page and the next is just going with the stress energy tensor correlation function. And Enrique Verdiger and his student proved that the symmetric traceless and divergence, right, this noise kernel, right, this is the 2-point function of it. Now, so with that, we have the Einstein Langevin equation. This is the familiar equation which you saw, for example, in Professor Taylor's talk after Bob's talk, the lambda and then alpha beta, but then here's this term coming in, okay? In general, it's a non-local dissipation in this equation. This is the Einstein Langevin equation in a simplified form, under the assumption that we're just dealing with gravitational perturbations, okay, of even a flat background, let's say. Well, here, of course, I've added on the curve background. And in the renormalization, you introduce these factors, the cosmological constant, and 2 of the 3, because the one is the Gauss-Bonnet identity. Okay. This equation in general has non-local dissipation and colored noise. Okay, so both non-locality and stochasticity showed up, and it will last us a long time to deal with this type of equation if you care to bring in the effects of noise and fluctuations. And I think after 25 years, this is about the time that we should deal with it. All right, now let's go back to the gravitational quantum cat. The fluctuation in energy density, and the centerpiece is the noise kernel. Since I'm running out of time in at least the time frame that I allotted to it, let me just tell you what it is, right? The simplest case is you can mock this up with a double well potential, right? Here's the probe or the detector. And we worked on both a classical probe and a quantum probe. The classical probe is less interesting. You can use quantum jump to deal with it. And here, the setup, there's just one parameter, right? So there's the distance. This is the minus and the plus that I showed earlier. And then let's just assume that the tunneling rate is given by mu. And there's the plus and the minus state. All right, so this is easy if it's electromagnetic. There's a long chain of 20 years of work of atomic cat state, right? Like Feynman, already, Nobel Prizes were awarded and so on. Okay, but here we're dealing with gravity. Okay. So let me just skip all these pages. We're doing it with non-relativistic and particle system. The thing I want to point out is the key now that you know, coming from the more sort of complicated backdrop of stochastic gravity, you know what we're looking for is the T mu nu T rho sigma, right? But then the dominant contribution is really the T00, right? T00 part, which is really the mass density operator, right? So then from there, we have the mass density correlator. And that's what plays the role. That's what determines the entanglement in the cat state. So that's the density, mass density, two-point function, right? So if you see that's the gist of the matter, and of course non-relativistic is a little bit easier. The stochastic gravity had so far been applied to early universe and black hole problems. But here it is a sigh of relief. We're dealing with a non-relativistic weak field domain. Okay. Nonetheless, that is the noise kernel. Okay. I just want you to know that that's the thing that actually is responsible for the entanglement. So the noise fluctuation give rise to gravitational cat state, the entanglement. Okay. This just explains that as a distribution. So, all right, so that's the answer, and it gives Rabi oscillation. So it's very similar to atomic cat states. Okay, so the big picture. Let me skip all of that top down and bottom up. It's kind of philosophical things. I don't mean it's not important. Probably not for this conference, but certainly very fundamental about whether gravity is fundamental or elemental versus is emergent. But even within the confine of our concern here, that is low energy gravity, how it impacts on quantum and quantum information. The question is, can we infer attributes of space-time fluctuations? Notice that's supposedly, right, space-time foam and Planck scale effects, right, from quantum experiments, even at the level of Newtonian gravity, okay, without appealing to AQT, because actually they turn this around and say, well, let's just introduce a noise and look at what happens. Can it help us resolve this collapse of the wave function problem? I'm going the more conservative route, and yet asking really revolutionary questions, let's say, right? Going from the, so, or even any theory of quantum gravity. Okay, I'll just leave it with that. And let me turn to Graviton noise, okay? Maybe in 25 minutes or so. All right, now, no, not even that, okay, maybe 20 minutes, okay. The effect on geodesic separation. And this is a very interesting paper to read. I highly recommend it, by Feynman-Vernon, okay. Basically is that it's just very difficult, right, to detect. And then Frank Wilczek and Bei-Lok, their group proposed that maybe we could look at the noise of gravitons, and in particular, the effect on geodesic separation, which of course is the setup for gravitational waves made so important by the LIGO discovery, right? So you should read this paper if you want to find out what goes on there. And there are two groups of papers, okay? And the result that I'm reporting on is in collaboration with Professor Cho, who's done a lot of work in the last decade related to stochastic gravity. Okay? And I will show you that actually, if you understand quantum Brownian motion using the influence functional method, which is pretty much identical to the closed time path or the Indian formulas, which is made very popular by Weinberg in 2005 in the cosmological correlation functions, okay, 2005. There are now many papers and monographs, the open quantum system, and so let me just flash through the key points in there. The key point is really the noise, as I said. We want full treatment, no approximation, no ad hoc, adding on anything without justification. Okay, how do we do that? So here's the one harmonic oscillator as a system, and then the path, made up of n-harmonic oscillators. We consider a quadratic coupling, so the whole thing is Gaussian. The beauty of that is that it emits exact solutions, and I want exact solutions because there's too many approximations. We don't know which approximation masks what real physics in their claims. Okay, I think I should just skip this also, but then turn to the crucial point. If you write, well, I can't quite skip it. Okay, anyway, the effect of the environment, okay, shows up in, if you expand this, the generating functional, right? And indeed, when I teach this course, I usually introduce it in the step back context, because students are more attuned to a wave function and psi star, right? Psi star, that's the density matrix. So it's the same thing here, right? If you go forward in time and backward in time. So usually I introduce the influence functional before I add on at the end. Well, it's really just the same as the Keldysh method, forward in time and backward in time. It's really the ingenuity of Schwinger in his 61 paper, which is really difficult to read, okay? Keldysh came 3 years later, but in condensed matter physics, they call it the Keldysh method. I don't know why they skip Schwinger. But anyway, all the environmental effects were lumped into this influence action, right? You can see here the functional integration over the Q variables, the environmental variables. And then in terms of green function, it's a set of 2 by 2 matrix. It's actually 3 of them because there is a relation amongst them. And then you can see there is a plus, 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 minus, okay? And it's in here that you can see the dissipation kernel and then the noise kernel. The difference variable, delta, and then the summation average variable, sigma, okay? So between delta and sigma is the dissipation, between delta is the noise kernel. So here, the Feynman-Vernon Gaussian identity becomes important. So this is the term that's pulled out, and you can introduce a probability density. And here is the first appearance of the stochastic force, noise, okay? So I just want to show you that there's no jumping around. Everything is kosher, right? And you can identify this, and you don't need to. You can carry on quantum field theory calculations. But if you prefer noise interpretation, which is relevant because there's so many papers using noise, okay? So this is the bona fide way of doing it, introducing noise. And with that, of course, the 2-point function and so on and so forth. All right, so, and once you have the influence action, you can take the functional derivative and get the Langevin equation. All right, so here it is. I mean, once it gets to this point, you'll feel very comfortable. The big difference is that our teachers who threw in that term, now you know where it came from, meaning the microscopic basis of this macroscopic Steinbeck equation, the Langevin equation. And there are many good things, okay, the Einstein Kubo formula and so on. So let me now maybe I should just even skip this. Historically, in the 90s, of course, we worked with the cosmological back reaction problem. And the interaction action is this H mu nu T mu nu form, which is familiar to all of you, right? But then the influence functional, at that time, I was thinking, well, quantum gravity, we don't know what's going on, but at least let's take something that we know very well, which is the simple mass movement or charge movement in a quantum field, right? So the system is well defined, and we could work out the whole back reaction, and we even have the quantum theory, which is quantum QED, right? So in the 20s, we worked on the second group of problems, which is a moving charge and mass in a quantum field with the same method, meaning influence functional, Feynman-Vernon, and then the CDP, Stringer-Keldysh, or the in-in. The interaction action, you can see also the simple source, right? Current, and then the field, okay? For a charge, it's vector, potential, and then H mu, T mu, right? This is what I showed you just now. Now, so that gives us the radiation reaction, the cell force, and so on, okay? I don't think anybody pay attention to these two papers because at least in the gravitational wave community, because why should we need a quantum field and so on. But now that's exactly what's useful for this graviton noise problem. That's why I mentioned it, right? So here, these set of slides are courtesy of Professor Cho. Blow it up a little bit, okay. So here, I'll just show you the beginning and then tell you the result, okay? Give you the result. Einstein action, Einstein-Hilbert action. We look at, let's say, the Minkowski space-time, weak perturbation with this graviton action, which is also very familiar to all of us. And now the system for us is actually two masses. If we fix the origin of a Fermi normal coordinate system on one of the masses, right, then we're looking at the geodesic separation. And the Fermi normal coordinate, of course, at every hypersurface is really the Riemann normal coordinate. You can recognize it by this Riemann tensor here, IJKL, and then 1, 0, and then 2 zeros, and so on, right? So the action of the second mass, also the simple one. And now in terms of gravitational perturbation, okay, we have the H double dot term, right? So this is the dynamic term or kinetic energy term. This is the interaction term. You can see the H coming in here with double dot, okay? Now, well, this is my slide, so let me shrink it. Okay, so our system is the geodesic deviation, right? The two masses, okay? So it's actually closer to the second group of issues that we study in 2000, the year 2000 in the PhD thesis of Phil Johnson, followed in 2010 in the thesis for Chad Gailey, okay? So for this problem, the graviton field is, we could express it in terms of the two polarizations being the massless minimally coupled scalar field. All right, and for this term, we could actually do the integration by parts and turn the two dots, the double dot, into one dot over z's head, right? So with that, actually, you can recognize the z dot as proportional to u. Z, by the way, is the geodesic separation, right, from the origin one mass to the other mass. And so it's really like the motion of a particle, in this case, the mass, the coordinate being z here, right? So it has this form, but the z is given like that. So if we go back and now invoke what we learned, I'm sure you will learn that quickly, the CTP, okay? Closed-time path formalism. Well, you can see that this J plus H plus, and it's always doubling, right, with the Stringer-Keldysh, the closed-time path formulation, and the 4 green function now in the 2x2 matrix. And here's the influence action. So again, notice that the difference variable and the average variable, right, sandwiched in between is the dissipation kernel. Okay, we change it to D, and the 4-legged animal because we're dealing with gravity, right? So, and between the two difference variables, right, we have the noise kernel. Here's this noise kernel. Really, this is the one thing that piece up these 3 topics in my title, in the title of my talk. All right, so you can see, and then the dissipation kernel and the noise kernel. One thing I didn't get to mention is that it's the retarded green function that enters into dissipation kernel. And for people in gravitational wave radiation reaction, it's very familiar to them because this is the guy that's really driving the whole show. Okay, directing the whole show. But of course, it's a lot more complicated than EM radiation reaction because there's contribution within the past light cone because of gravity, the scattering and all of that. So that is responsible for dissipation. And here's the Hadamard function, which is responsible for the noise, okay? And those two are the essential ones. And in fact, there's no randomness, there's no arbitrariness in this because they obey this fluctuation dissipation relation, the slide that I skipped over, okay, very nicely. And in fact, this is fully non-equilibrium, so it's really an upgrade of the fluctuation dissipation relation that you're all familiar with from linear response theory. Well, since I mentioned that, I should also add that this upgrade is totally different because most of the things that we learned in textbooks were based on linear response theory, which means that you need an equilibrium state, which unfortunately in cosmology, at least, we don't have. And if you're interested in the back reaction effect on black hole from Hawking radiation also is a dynamical problem. And we cannot stay in the goodness, the comfort of an equilibrium configuration relying on linear response theory. That's just a remark for all the challenges in the future. All right, so remember this noise, right? So this term is what we can use the Feynman-Vernon Gaussian functional identity to introduce noise. Okay, very restricted, okay? There's no arbitraries in here. But once you have written it in this way, then you have the stochastic effective action, mainly, I mean, we're turning those two terms, you're substituting and introducing this stochastic source, right? And then we have the Langevin equation. Notice the dissipation kernel and then the noise kernel. Okay, so here now coming back to our comments later, right? The second term in this equation. And without the graviton effect, we have the homogeneous equation, if you want to follow that exactly. And then we do a background field decomposition and just assume that the background classical is equal to 0. You can always put that on, it just tags along because it's a classical quantity. The main focus is actually in this fluctuation term, right? It's quantum in nature. So it's delta Zi, that's the equation that you saw. Blow it up again. Sorry about this. Right, so with this condition, we have the geodesic separation. That's the solution, and then the geodesic separation correlation. So this is what we're after. So it boils down to calculating the noise kernel. And what Hing-Tong did, it was mainly his calculation, I should say. I'm always happy to say. We considered Minkowski vacuum, thermal vacuum, and then coherent state, and then squeeze state. So it's pretty much all that matters. And in short, we found out that the Minkowski vacuum, not unexpectedly, is very weak. And at high energy and low, high temperature and low temperature, for the thermal state, right? Low temperature proportional temperature cubic power, and high temperature at 5/2, a little bit of a gain, but we're not operating at such a high temperature. Coherent state doesn't come in because it's basically like classical feature. The quantum aspect, especially quantum noise, would not show up too prominently. So the only hope, and that was, of course, the important proposal by Molik and Frank Wilczek, that group, is that look at the squeeze state. And sure enough, the result is that the squeeze state enhancement has this exponential factor compared to the Minkowski result. Now again, okay, if you're familiar with squeeze states in quantum optics, this is no surprise, okay? And of course, in quantum optics, they have ways to prepare squeeze state. Do we have it? Not in the lab, but the early universe, conveniently. Inflation, depending on how long the inflation era would be, and that depends on what kind of field theory you assume, single inflaton, multiple inflaton, and there's just a zoo of models you can choose, and you can come up with the squeeze parameter. So if you combine these two aspects, there's hope that maybe, okay, from the early universe, from future cosmological observations, there's a chance that we could find out the noise, right, of gravitons, primordial gravitons, and from there, we could say something, or maybe even affirm that graviton, well, graviton feature, right? There is a quantum nature associated with perturbed gravity. I have to emphasize perturbed gravity, okay? That's another talk altogether, because these days, because people are getting very excited about the cat state entanglement due to masses, and rightly so, I think it's a good direction. But then there are people who jump to the conclusion that this is quantum gravity. If we adhere to the definition that it's about quantum gravity theories are about the fundamental structures of space-time functional at the Planck scale, it is not, it is perturbative gravity, and you quantize the perturbations, which is really graviton physics. And I think that's it. Thank you very much.
Okay, thank you. Thanks a lot for this very nice overview. And it is now time for questions or comments. So anybody in the audience?
Let's see, I should stop sharing, right, in order to see the questions, right?
Oh, okay, there is Ericsson. There is a...
Yeah. Yes, can you hear me?
Yes, I can hear you loud.
Hi, yes, thanks for a very nice talk. So I just have one small question regarding near the end, where there's a choice of squeeze states, vacuum states, and coherent states and stuff. So one thing that I have never been very clear about is that whether there are arguments about what kind of sources that will give certain kinds of state. For example, the primordial inflation, right? There is this story that I always say that, you know, the squeeze states, large squeeze states could be produced there, but I'm not sure how the connection was made there. Like, how do I know it's going to produce squeeze states?
Yes, right. It gets back to particle production in the early universe, okay? And this is what everybody loves, quantum field in curved space-time, okay? So when there is, in fact, it's more general, when there is parametric amplification, okay, then you can get from a, you know, a vacuum state would be squeezed, so to speak, okay? So the early universe is really, doesn't have to be early universe. Even in an expanding universe, the vacuum state would be squeezed into a squeeze state. Now, but of course, of significance, one would have to attribute inflation, because for 60 folding time and so on, it will be significant squeezing. So if you want to, you can read the papers, of course, by Leonard Parker a long time ago, but also the paper by Grishuk and Sidorov, which explains that why cosmological particle production produces squeeze state, right? But then there's also the gravitational perturbation part, because it's quantum nature, right? It comes from all these structures, come from quantum fluctuations. So there's also that which will be squeezed along in the fluctuations.
Okay, thank you.
Or Steve has a hand.
Any other question?
Steve Fuller.
Comment?
Yes, Bei-Lok, I understand why the cat state gives a problem for semiclassical gravity, semiclassical Einstein equations. And I also understand why you don't want to go to full quantum gravity to resolve that. But I missed your message, I think, of how does the stochastic approach solve the problem? What does it tell you about cat states?
Right. Yeah. I could even just say the cat state, of course, is defined as a superposition between plus and minus, let's say, right? Yeah.
Okay.
And Larry Ford actually had a paper, which is very nice, right? He's pointing out that if you take semiclassical gravity, you average it, and then your prediction is that the cat is located at the origin. Stochastic gravity starts taking
Halfway between the two.
Which is wrong, of course, right? Which defeats the whole purpose.
Yeah.
That's right.
I said that already back in 1973 or something.
That's right. We love quantum, so we're anticipating this sort of thing would come up, and so stochastic gravity, to put it simply, takes into account the T mu nu T rho sigma, right? So the correlation enters, and another way, as I mentioned in passing very quickly, is noise or fluctuation. So these two are actually equivalent. On the one hand, it's the correlation of the T mu nu, and on the other, you can come up with the noise kernel, and it's the same thing. So you're beginning to see something different from the average, so to put it mildly.
Okay.
Ivan.
There is another question by Ivan Agullo.
Hi, Bei-Lok. Thank you for the nice talk. It was a very
So we corresponded through email.
right. It was a very nice talk. Thank you. I have just a very quite general question about the stochastic program, and it has to do with symmetries. So imagine that you have a quantum state which is, let's say, homogeneous and isotropic, like any of the cosmological vacuum that we use. And then you compute the stochastic term, and as a function, is not isotropic and homogeneous, but as a probability distribution is. So my question is whether such term can induce, can break the symmetry of the gravitational field. So
let's go back all the way to quantum field theory in curve space, right? Whatever you do there, right? So usually, while this gets back to Steve's Frohling's thesis and so on, you need to find the right symmetry in order to write down semiclassical Einstein equation, right? In the choice of the quantum state and so on. So we have no problem with that. And all along, you can just push this up one round to semiclassical gravity, and then also in stochastic gravity. There's a slide which I show you quickly, and it's thanks to the work of Enrique and his students. He actually proved everything is kosher. Whatever we do in quantum field theory, you can actually have all those nice properties in the noise kernel, symmetric, trace-free, and so on. Yeah, so also with the symmetry.
okay, so then if the quantum state has certain symmetries, the metric you get out of it using a stochastic gravity will respect always those symmetries.
Absolutely. And those are the things that I've watched very closely in the 90s. Otherwise, it becomes arbitrary. Yeah. So the basis is still quantum field theory in curve space-time.
Thank you.
Okay, thanks, Ivan, for your question. Any other question? Okay, let me ask you one last question. I wonder whether the gravitational noise, the quantum noise, could be in some sense relevant for the studies of the the classical studies of correction for the self-force approaches to the two-body problem.
Oh, the self-force, right?
Yeah, the self-force approach for the two-body problem.
Yeah.
For instance, when one object is very massive and the other is very light, and then the time, I mean, it could be some accumulative effect because
Yes.
the time of the orbit is long, it takes a long time. So if there is some change to get some tiny effect of this noise, the quantum noise.
Yes, that was what we wanted to do in the year around 2010. And it was done in Chad Gailey's thesis work. As I mentioned in passing, the 2005, 2015, and 2016 papers, probably nobody paid attention to. But that's precisely what the solution to your problem. Okay, so in 2000 and I forgot the year now, 2009, something like that. 2000. Okay, so later after that, we actually had a paper indicating the extreme mass ratio between two masses, and you can work it out completely almost. Okay, so this is a different approach to the well-known problem, right, in the gravitational back reaction or the self-force problem. Yeah, and the next thing that I wanted to do, of course, there are too many other things, was actually to check with the two-body effective one-body approach in that limit.
Yeah.
Yes, the answer, yes.
Yeah. Okay. Okay.
I can send you this file and the references in there. Yeah.
Okay. Thank you very much.
Sure.
And well, thank you very much for your very nice talk. And well, hope to see you in another meeting.
Thank you. Thank you all. Thank you all.
Okay.